not the variable, next week. So we're going to start looking at discrete random variables. We take some of the concepts of probability and start turning those into things that we measure or record. So if you think about their distribution and the chances of different outcomes or things that you might measure in an actual study. Right? So we're going to talk about discrete random variables. They have probability distributions, and out of those we're going to compute summary expected value variance that might go there. And then we'll look at a little bit of what can be done on the computer in terms of displaying these or simulating a few of these, kind of as an introduction to using the computing. We'll do more with the computing next Tuesday to kind of ramp up and see about downloading the program and getting all that work done. So it's kind of a gradual thing to do. So a random variable is some random phenomenon. Hello, here you go. And the random variable records a numerical outcome. From a random process or random phenomenon. And the discrete random variables, they have a countable number of possible values that they can take on. So it could be just some integers, 1, 2, 3, 4, 5, 6, or kind of implied positive integers or non-negative integers might be possible. So it might be infinite, but just countable. It might be, fractions, decimals. It could be countable, right? So it could be that more often it's some integers or specified values of things. Often we refer to the variable as, in symbols, will be some type of capital letters for the variable itself. The values then might be represented by lowercase numbers in formulas and symbols. And other times we're just going to, for the initial examples, just show you, some numbers and some examples and not deal so much with the general symbols for things, right? So as an initial example, imagine that we're going out someplace and we're going to invest the money and drill for oil, and drill for oil. And we could be, if we have some success in drilling for oil someplace, in one scenario, imagine then we earn $1,000. Right? And 1,000 is just a number putting in there. Right? Maybe this is more realistic if it's in millions or tens of millions, makes it more interesting with higher stakes. But there's some positive gain if there is. That's if oil is present. If we have a failure, right, and there is no oil, we have gone down $100 because we had that initial investment, right? So this could be a random variable. You could call this a random variable X as the dollar amount that you get in the scenario, and it has two possible levels, right? You could have a different scenario. Imagine a different scenario. Y, say you drill for oil, but it's a little bit different. You're dealing in different some areas. So if it's successful and there is oil, right, you still get $1,000. Right? Maybe that's a big oil response. If you have a smaller response, and so there's a little bit there, but not quite a big one, maybe you earn $100. Right? And but if there's no oil, right, then you've lost your $100 in investment. Right? And so that would be another variable. Maybe we'd call the outcome in this something like that. Right? And random variables are going to have probabilities associated with their different outcomes. So let's imagine that we dig, and then 10% of the time, right, we get $1,000, right? But then 90% of the time we get this, and so those could be probabilities associated with those two outcomes. Right? Random variables in this case, we could make our probabilities of these different outcomes. So imagine at 5% we get the big oil happening, right? But 15% of the time, so I'm not directly splitting that 10%, I'm just imagining a different scenario where maybe we get some natural gas or something else out of that well that gives us some money, right? And then 80% of the time, right, we get those different numbers. Right? So in the first case, we have two values and their probabilities. When we have the values and the probabilities, it's called a probability distribution. So a probability distribution right, for a random variable. It's a list of the possible values that you can get, and then the corresponding probabilities. That are there, right? And based on that, we can, look at these different random variables. Right? So one way of looking at that would be make some type of graph. You could graph the possibilities. So here is 1,000. Let's say here's 0, and here's negative 100 would be a little bit closer than that thing. We can have our dollars there, our values on this side. So in that first scenario, those values, the random variable is called x, a little x there, and then the probabilities of those values that the random variable equals a certain value. What did we say? We go up to 90%. So if this is 0.9 as a probability, 0.1 might be somewhere down there. Right, 90% of the time we don't, we're losing out and it's not working out. And in this case, we get some probability that we get this big payoff, right? In this other situation, where the other oil scenario, try to make these things kind of comparable. So I'll put 0.9 up here, 0.1 about there, right? Negative 100, 0, 100, and then 1,000 out here somewhere. Right? Now this variable had 3 probabilities, right? An even smaller one out here at this, at 1,000, it was minus 100. Somewhere it's good to put that it's in dollars. This would be, this axis would be the probability that our random variable takes on one of its different values. And we said it was 80%, let's say if that's 80% there, a little bit below that one. And then 15, so a little bit bigger, oh, not at 0, it's at 100. Where you get a little bit out of that, but not much. So we have two different graphs there. All right. So would you want to invest in either of these scenarios? Maybe, maybe not, right? So something we calculate based on random variables to describe the pattern. You have the values, you have the probabilities. This can be called expected value. The random variable. This might be called the mean or average value corresponding to that random variable. Almost always I'll abbreviate random variable by RV instead of rewriting that. And so this is given in a symbol, an expectation, capital E of the random variable. Right, it's going to mean the mean or average. Right. It's weighted average of the possible values. for a random variable, and it's really weighted by the probability. So a probability weighted average of the possible values. So in symbols, say we have n possible values, and they're x1, x2, right, up to xn are possible values. Well, we take those possible values, these x of i's, times the probabilities that we get those values. So we add up the xi values times their relative probabilities, and that gives us kind of a weighted average of the different ones. So more weight on the values that are more likely, less weight on the ones that are rare. And that describes a mean average of those values. Not equally weighted because the probabilities are different. Right? So how does it work out for our oil scenarios? So what this formula says for our oil scenario, which is the first one, the expected value of x. Now we have two values, so we have 1,000, right, and negative 100 as our values. Right? We don't want to directly average those because they're not equally likely, right? What did we say was this one and the initial one? Wait, one. Yeah, 10% for this one, and then 90% for this one. So that's 100. This is minus 90. So it seems to have an expected value of $10. So that's good, right? That's positive, right? It's above zero. So that would suggest that if you could do this investment, that your expected gain each time you do it is $10. Sometimes you're going to get 1,000. Sometimes you're going to lose $100. But the interpretation of the expected value is that if you keep doing this over and over again, right, many different wells, different investments, that in the long run, about 10% of them are going to be 1,000, and about 90% of the time you're going to be losing that money. But the way it would all add together, in the end, you get about $10 per time. Right? So that would look like a good deal. Right? That, you have to possibly endure some risk, right? So you only have a small amount to begin with. You could lose 100 many times before that 1,000 would come in. Or maybe you would be lucky and get 1,000 right off, pretty soon. But it's if you can keep going for a very long time, on average, you're going to end up with $10 gain. Right? How about the second one? So this is the first oil situation. Here's the second oil situation. That we call y. What's the expected value or average value of y in this case? Do that one. Write down some of the formula, right, to see how that goes. Let's look over this briefly. This one looked like a decent investment. So we had 1,000, 100, and negative 100 as values. Right? And probabilities of 5%, 15%, and 80%. So multiplying this about 5% here of that is just 50. 15% of this is 15, and 80% is minus 80. So that's 65 minus 80. That's a negative $15. Right? And that's not good. You wouldn't want to invest in that second one, although you could get $1,000. If you do this over and over, you're eventually going to come out negative. Right? So the first one looks like a better investment than the second one. So these expected values give some comparison. But any questions? Graphically, where did that expected value come up? Right, that expected value in this first case was $10, was about there. Right? And the expected value for this one was actually a little bit below 0. That if these things were weights, and kind of positioned at that place with kind of relative weights at these things, these weights would be kind of where that would balance, right, under there. Right? You move it over here, or you tip down that way, you move it over here, or tip that way. So this is actually kind of a balance place, kind of as an intermediate place there kind of on the graph. Right? Sometimes you'll have a value near that mean, and sometimes you won't, but it's just that's the way it goes. So let's look at another couple examples for comparison. Right? Well, let's say you take a random sample of cars and you record the number of windows out of 4 that are open as people are driving around. Right? Something about behavior, something about energy efficiency could be be part of this whole big study. Right? And so let's say that in one scenario we're looking at the summertime, and then another one is in winter. Right? And so what are the possible values of our random variable? And I'll call this one, this random variable S, and this one I'll call W. You can change those letters to match up to your scenario. X, Y, Z are just defaults, but you can also specialize it, right? To make it more meaningful, easier to talk about with the symbols. Right? So possible values. Each car has 4 windows.
0 through 4.
Yeah, 0 through 4. Right? Yep. 0, 1, 2, 3, and 4. Right? And this one are the possible values. To get a probability distribution, we need some probabilities. Right? So let's say that 40%. Right, 20%, 10%, 10%, and 20% are the different probabilities. Those should add up to 1. So 60, 80, that adds up to 1. In the wintertime, let's say you get 55, right, 20, 10, 5, and 10. Right. So how do these distributions compare? What are something that you notice about the differences here? What would be an interesting feature? So this might be, maybe this is obvious, maybe it's too.
There's some pretty crazy people in the winter.
There's some crazy people in the winter with some windows open.
You see them out with one window open.
Yeah. So it's kind of that. There's a match there. So using your descriptive ability and in your language, you can pick up on these different things, right? So probability distributions tell us the likelihood of different values, and we're interested in those in different cases, right? So if it's really hot, maybe these people are running their air conditioning, maybe these people are running the heater, but maybe these people have problems with their windows being clouded or something. But so there's differences. 0 is more likely in this winter time. 4 is more likely out there. So all of those things are relevant as you're looking at distributions of values or probabilities. Just that basic description conveys something and could be interesting. So in large surveys, if you're asking how many times does somebody go to emergency room visits, right? If you're doing a survey of veterans and veterans health care, right? You could be looking at 0, 1, 2, 3, and 10, 20. Some people could be going a lot. And that distribution of values and their relative probabilities is of great interest. This is a little more artificial example, but you could be really interested in talking about those probabilities. Which one do you think has a larger average? Summer looks like average. So we expect that the expectation of the summertime is greater than the expectation of wintertime. We can check that. Right, so the expectation of summertime, right, 0 times 0.4 plus 1 times 0.2 plus 2 times 0.1 plus 3 times 0.1 plus 4.2. Right, so here's 0, 0.2, 0.2, 0.3, 0.8, and that's what 1.5. This is, the units here would be windows, right? On average, 1.5 windows are open, right? 1.5. Right? We're not counting whether it's partially open or all the way open or anything like that. Of course, you maybe could do that, but this is just any bit open counts. The expected value of W, if you do that same sort of thing. Let's see, what was it? I did it here somewhere. We could do it again, but maybe it's easier if I just W 0.95. Skewed towards more at 0. Yeah, so the average is higher in the summertime. Right. Almost 50% higher. Well, more than 50% higher. If you wanted to compare these, you could do a graph some way. Try to put them together. 0, 1, 2, 3, 4. Labeling the graphs. Right, number of windows in the highest percentage. So this is 0.6. So 1, 2, 3, 4, 5. In the winter time, winter's colder, so we'll make that a blue color, and up to 0.55, 0.2, and it was 0.1, 0.05, and then 0.1 again, kind of like that. In the summertime, right, warmer, this was at 0.4, 0.2 again equal 0.1, and then 0.1 and 0.2, so a little bigger out there. And the average for summertime here is 1.5, and that average for winter time was here about 0.95. So it gives a little bit how this compares. Right? In the veterans case, right, so there was news about veterans health care the other day that they're changing some of the rules so that veterans that live a long distance or have a particularly long wait to go to a local veterans hospital can now start to go into more private care, right? To expedite things so people don't have to wait quite as long, right? So if this was, the days that, the number of times that people go to emergency care, right? You could look at one area that has generally less crowded versus an area that is more crowded, and then you'd be interested in these distributions of how many times people are going, or what's the average wait time for different people. But any questions about expected values for this? A different thing we can do is look at variance. For random variable, and also the standard deviation. Of a random variable, right? So when we can be interested in the spread, how diverse the values are. Right? And so variance of a random variable, either written as VAR or just V of one of those two. Right? If you look at different books, some will write VAR, some will just write a V, right? But it's the variance function. Variance is going to compare the values versus the means. And to measure spread, we square all these things and then take the expectation of that. Expectation of all that. The standard deviation is the square root of the variance. As a measure that describes the probability distribution. Right? So when we take the expectation of a function, more generally, you take the values that you can have on that function weighted by their probabilities. Just like the expectation of x, you took the values times the probabilities. Here we're going to take the values of this function times x. So we'll illustrate that for that and then talk a little bit more about this computation. Right? So for the windows, the values of 0, 1, 2, 0, 1, 2, 3, 4, the probabilities. Let's do first the, I get this here for the winter time. Had 55, 0.2, 0.1, 0.05, 0.1. We calculated that the expected value of W was 0.95. 0, so 0.2, 0.2, 0.4, that adds up to 0.8. That is in 0.15, so you have 0.95 windows. To calculate the variance of that, we're going to take the value minus the mean, right, and square those values. So we would take 0 minus 0.95 squared, right, for the first one. 1 minus 0.95 squared. 2 point minus 9 squared, and then I knock it all right there. 3 minus 0.95 squared, and 4 minus 0.95 squared. So this W minus the expectation squared means calculate those values. Now the expectation of that is we multiply each of those by their probabilities and add them up. Okay? So this 0 occurred with probability 0.55. Probability 0.55. This one occurred 20%. So 0.2 times that. 0.1 times that one. This one was 0.05 times that, and then 0.1 again. So it's a weighted average of these squared deviations. And that's the variance. The variance in this case, that's the variance of the number of windows in winter, turned out to be 1.75. So that's just as a number. It has units. What do you think the units of measurement would be on a variance like this? The values. Number of windows, the expectations number of windows. The difference from the average would be number of windows, but we square it, right? So windows squared, it's not something that we really can use. We could compare it to the summertime value, and that'd be a meaningful comparison, but the units don't have much intrinsic meaning. The standard deviation of the number of windows in the winter time is going to be the square root of the variance, so square root of 1.75, which is 1.32 windows. That's back on the scale of windows. And very often the standard deviation is a little bit easier to work with in terms of thinking about actual measurements. Right? There. How about in the summertime? Do you think the summertime will be more variable and have a higher variance measure versus this? Yeah.
I'm just confused, like what 1.33 windows like is representing.
So, right, so it's a standard deviation of the values that we would have. So it characterizes in one way that probability distribution, right? So looking back at our picture, right here, so this was the blue was summer and the red was winter, right? So as we get values from this probability distribution, we'll get zeros and ones and twos and threes and fours, right? And so if you did that, you got a whole bunch of cars and you got those standard deviations. What would the standard deviation of those values look like? What would the measurement of spread kind of look like, right? And so we can calculate, we had a bunch of values, we can calculate the sample standard deviation of just those values. Right? On the other hand, we have a probability distribution, which tells us theoretically a certain percent of times we're going to get one or zeros, ones, twos, and so on. What would be kind of a comparable measure of that if we had a big sample that was proportional to our actual probabilities? And one other way that we will, so it kind of just describes the spread, right? If one distribution is more spread out with its values, it's going to be bigger standard deviations, bigger variance, and get a bigger measure. Okay. So if one veterans hospital is better at controlling things and treating people so they don't have to keep coming back again for multiple visits, it would have less extremes and probably have smaller variance, maybe a smaller average as well. Right? And so it could be meaningful. The other way that we'll use this mean and variance is that in a lot of cases, particularly ones that have more and more values and more, if we're taking the total number of windows or the average number of windows in many cars, and we made a histogram of a bunch of values, and maybe something like it wouldn't necessarily be perfectly symmetric like this. But if you take a bunch of values, and this is a little histogram of their outcomes, that very often, if you have the average here, that a lot of the distribution of values is kind of the average minus about 2 standard deviations up to an average plus about 2 standard deviations, covers usually a lot of the space of values. You can have ones that are, of course, further out there. This doesn't work as well for things that are really bounded so much, like the 0 to 4. You're not going to get that exactly. And it doesn't work so well if your collection of values is kind of skewed, because then the average is a little bit lower. You can't really go, doesn't make too much sense to go down to. But we will have a couple probability statements that we'll make about how things are, the mean plus or minus a couple standard deviations, or plus or minus 3, describes a lot of the possibility. Right? So we apply that in the winter case. The picture, the average was 0.95, right? And the standard deviation was a little over 1. Right? So if you go down 1 standard deviation, well, you can't go any more than that, right? But if you go up a couple standard deviations, one point something, right? You get up here where most of the actual values, the zeros, the ones, and twos, threes are. There are a few cars that have the 4 windows open, that's a little bit larger than that cutoff, but it kind of gives a little bit of guide for that. I wrote the wrong letters here. The winter time is cold, and the summertime is hot, right? So that's to be reversed, right? So of these two distributions, which one looks more variable? Which one do you think would have the larger standard deviation? Winter. Why do you think winter would have a larger standard deviation?
Because a lot of the bars are really close, except for 0, winter's substantially higher.
Yeah, so substantially higher, right? So if you look at the standard deviation, the spread across these, the likely values you're going to get. Which one is going to give you, when you have a collection of cars, which one is going to give you cars that are concentrated in one area versus cars that are spread over the whole range of 0 to 4? It's a little hard, I don't know, to phrase. So in the summertime, sometimes you're gonna get zeros, but then you're gonna get 4 and everything in the middle. Right? In the wintertime, you're gonna get a lot of zeros, a lot of 1s, and a few that are up there. So the winter is more skewed in the sense that it's concentrated down. But a lot of the values are coming in at 0 or 1, having a more narrow range. Whereas for the summertime, the red ones is you have things at the more extremes. So it turns out, right, that the variance for, that's the winter time. Okay? So the winter versus summer, the averages was 1.5 in the summer and 0.95. Right, so the expectation. The variances end up being larger actually in the summertime. This was 1.75. You do that same calculation, you get 2.45. And so the variance is bigger there because you get zeros and 4s, you get things more on the extreme, so the points are spread out, the probability is spread out. Everything's between 0 and 4, so it's that same range. But the outcomes are spread a little bit more. So the standard deviation, the square root of that, this is 1.32, and this one's 1.57. So it is a little bit bigger in the summer. Right? In there. But some of that description that, you were describing what happens correctly, that the winter gets piled up at the zeros and 1s and are there, and occasionally there's these ones that are out there. They're just occasionally out there and not too far away, then the variance doesn't go up so much. Right. So, any questions about it so far? You can apply this to some other scenarios. So, another particular type of variable is called Bernoulli. Bernoulli is named after Jacob Bernoulli, and in this case, others use x, a random variable x. It takes on 2 values. This type of variable could be used for yes or no type questions, classifying people, are you a veteran, or you're not a veteran, female, male, yes, no to a political question, opinion question. Right? And the probabilities that are associated with these, to get the probability distribution, is some value p, and then so the opposite of that is 0, that it does not happen, is 1 minus p. So this could be corresponding to yes and no, or something like that. It might be success. You successfully treated a patient and they've gotten better, or no, they haven't got better. Right? So yes and no could be a binary outcome of that, and so some probabilities p and 1 minus p. And so that's called Bernoulli. What's the average value of a Bernoulli random variable? What's the expected value? Yeah. The general formula is you add over all the different possible values times the probability, and it equals this. In this case, there's just 2 values. So the first value, as I listed there, is 1. And times its probability plus 0 times its probability, and so it's just p. Right? That probability is just is the average value. You get success a bunch of times, right? And failure some other time. On average, you get that. So sometimes we'll take linear transformations of random variables. transformation is if you have a value, so you have a value x, and you're going to transform it to a new scale. You're going to do a plus b plus x times a, something like that. You can add a constant to it. You can multiply each value by something like that. And if you apply that to the measurement process, we can get new random variables. Right? You could measure something, say on a success-failure scale, 0, 1, and then scale it in a certain way to get a new variable. Right? And so in the oil situation, right, the first oil situation, right, we said that now we're not going to use the same y and x. Right? So we had success, you find oil, or you have a failure. That could be given, a code of 1 or 0. And we said that the probability of success was 10%, right? Or the 90% chance of failure. This could be our probability p, this could be our probability 1 minus p. Right? And so if this variable is what we're going to call x in this case, right? Not exactly the dollar amount variable we had before, but call it x. Right? The expected value of x still has meaning, the mean or average. Right? So each time we do this, we're going to get zeros and ones. We do it 100 times, we get 100 zeros and 100 ones. Right? How many of those do we expect to be ones, and how many do we expect to be zeros? The proportion we expect to be ones and zeros is the expected value in this case, right? So, right, 1, 10% of the time, 0, 90% of the time, and so the expected value is just 0.1. Now, if we want to convert this to a dollar amount, right, how do we have to transform it in terms of a linear transformation to produce the dollar amounts that we have before? Right. We need to write an equation that will take the zeros and ones and map it into the dollar amounts before. Right? So we're trying to map it into dollar amounts, right, that are $1,000 here and negative 100 here. Any suggestions for our A and B values for our intercept and then essentially a slope or multiplier? Yeah.
Would our intercept be negative 100?
Yeah, so if you make it negative 100 for A, so negative $100. And x is 0. Well, if x is 0, that goes away. Our value of x is 0. We're left just with that intercept. So 0 has to go into that, right? So what has to be that value of b to make this work out?
1,000.
If it's 1,000, right? Right? And you had a value of 1, it'd be 1,000 times 1, but you'd still be subtracting that 100. Right? So we want it to be 1,000 in the end, right, after that. So what if we make it 1,100? So now if we have a success, right, our equation would be to put a 1 in here for that value, so we get 1,100 minus this 100. Presumably that's the cost of setting up the operation, that kind of a fixed cost. And if we're successful, we recoup that investment, plus we get another 1,000. And that's what was originally recorded in this scenario. And so that's an equation that converts between 0, 1, success, failure. Did you strike oil or no? Right? Is it a dry hole out there? And then for the dollar amount conversion, right? What's the relationship between the expected value of y, right, and the expected value of x?
They're the same.
Huh?
Are they the same?
No, there's a relationship between them, right? Almost, right? If we go back to the formula, in the the general case. This expectation meant take the value you can have on y times the probability of those values over all the different possibilities we have. And we're doing discrete variables, so we can count them. Yeah, this is even saying it's a finite number of values, but the general case will work. Right, this equation that says y equals a plus b times x, right, it also applies to these values. So each value of x that's possible, you'd multiply it by your scale factor and add your constant, right, a linear thing. Or you can even graph it if you want, right? So there could be a graph, here's x and y, and then there's some equation here, y equals a plus bx. And so each value of x gets mapped into a value of y. And it's doing that linear, the straight line equation there. So, right, if we have this equation for x, we can substitute a plus b times xi times the probability that y equals a value. Now, as we're doing things in this discrete, right, these are one-to-one transformations. Right? For each value of x, we get one value of y. So this is a plus b times xi. It's equivalent to the probability of that xi, right? Because xi is, take yi minus the intercept divided that. There's a one-to-one mapping between these things. So the probability that y equals a value is exactly the same as the probability that x equals a value, right? So in the oil case, right, you're successful, you get about 1100. You're not successful, right, you get the negative 100. There's a one-to-one thing there. The probabilities don't change. What can we do with this type of equation? So that's a summation of terms, right? So the summation goes over, right, all of these terms are together here. Right?
Can't we pull one right now?
Yeah, we can distribute that, right? So split that up. We can split it into two, and maybe pull some things out, right? So we can write this as an a times the probability that x equals that value. And then we can have a second one, right, where it is I equals 1 to n of b times xi times the probability. So if you're doing a summation like this with a constant times something, that's like a times the probability is the first value, plus a times the probability is the second value, plus a times the probability is the third value, and so on. We can pull that a out. Pull out a times the probability that x equals xi. Over here, we can pull the b out because it's just a constant. And every term is multiplied by b, so b is just a constant. So you can factor out that constant. And there's xi, probability x equals xi. And can you simplify this a little bit? What should this summation be? What does this say do? Over all the possible values you can have for that variable x. In the oil case, there were just 2 cases. In the Windows case, there were 5 variables, right? If you add up all the probabilities, what do they have to add to?
1.
They have to add to 1. Right? So this has to be a. And what's this term? This summation over here. Xi times its probabilities, added those together and part of that weighted average. That's the expected value of x, right? So we started off here, right, looking at the expected value of y. So it turns out that if there's a linear transformation, the expected value of y equals a plus b times the expected value of x. And the linear transformation goes to, sometimes I think of expectation as a linear operator. It takes values and probabilities and produces a weighted average. And if there's a linear transformation, you can first change all the values and then do the expected value. Or you can choose the expected value of x and just transform that. Right, you get the same answer either time. If it's nonlinear, like if we had squared the x's or taken logs or square roots or something, and it's nonlinear, this doesn't work. It works if it's a linear transformation, like going between temperatures or scales or something like that. Right? So we had x had a value of 1 or 0 with probabilities 0.1, right, and 0.9. The expected value of x was 0.1. P and 1 minus p for these Bernoullis. Right. Right. So, and then y, there's negative 100 loss if you aren't successful. You get $1,100, 1,000 plus recovering the $100 cost here. So if we calculated this, what is the expected value of y according to this linear transformation? Yes.
Negative 100 plus 110.
Yeah. So negative 100. So a is the negative 100 plus this thing times the expected value of x, right? So x goes in here. B is 1100 in this case, and so this whole thing, negative 100 plus negative 100 plus 110, right, gave us our $10 value. At the beginning, when we took expectation of that variable, we got 10. Right? We took 10% that you have 1,000 in the end, plus 90% that you were negative 100. So this was 100 minus 90, which was our $10. So this one is going directly from y, and this one is $10, not this. And this one's using the linear transformation. Sometimes it's easier to do things on one scale and transform them, or you might be given information on one scale and you want to change from British units to metric units, or something like that, or put a dollar value in there. Think about the chances, and then do a dollar translation and make it work out like that. But any questions about?
Can you go back one slide?
Yeah. So we asked what's the expected value of y. That's the general formula. But we have this relationship that y is the linear transformation there. And we argued that the chance that you have a y value because of the discreteness of the one-to-one relationship is at the same probability as the corresponding x. And then a little bit of work to split up the algebra, rearrange terms, distribute things there to get a plus this, and this thing was 1, because that all probability adds to 1, that's 1. And then this part over here is the expected value of x for that. So we get this relationship that you work for x and y being discrete and a linear transformation of any type you want. You could have a negative slope if that was of relevant. A and b can both be positive or negative. You could also have a be 0, right? And then you still get the scale change. Yes.
Does the linear transformation always fit?
Not necessarily. I mean, so this one is doing the 0, 1 variable to a dollar value successive, right? But in other cases, it might not be. Relationships might be nonlinear. Like if you're actually looking at data, right, between different things, you might have a nonlinear relationship, and then you wouldn't want to directly transform, right? But if there's a scientific or conceptual reason why you're doing it, this is how it would work for those variables. How about variance? Y equals a plus bx. What's the variance of y? We didn't do variance of, well, we can do this general case, and then we'll, yes.
Wait, I'm sorry. Can you just go back one more slide to the transformation
This is
solving
the-
for EY?
This one?
Didn't we solve the $10? Isn't that E of X?
$10, yeah, it was called, I'm sorry about that. It was called X before. I did X and Y, and this one, Y is just being called, I'm not connecting exactly between that. Think about this as a new case, that the expected value in the dollars. So this is the expected value in the first oil situation.
Oh, so we're going back and forth between dollar and probability within one of the cases?
Yes,
Oh,
yeah.
okay, thank you.
Now, if I had kind of foreshadowed, foreseen, I could have maybe done a better job keeping those separate.
No, that's fine, thank you.
How about variance? What happens with this? So variance, right, is the expectation of y minus the expectation of y. That squared the expectation of that whole thing. Now this one, before jumping to writing down the summation formulas, let's do some of our substitution. We want to know about spread on the y scale, but what is y? Y is a plus b times x by this linear transformation that we're doing. What's the expected value of y? We figured that out, right? Expected value of y equals a plus b dx. Oh, sorry, times the expectation of x here. So we could put that in there, a plus b times the expectation of x. That squared. So we can do a little cancellation, right? What cancels?
A, B, A plus.
A cancels. A, this is minus A here. So A is completely gone. And this is B times expectation of X is here. And it's a square and that. So the variance is about spread, how far our observation values from the center. Right? So if you add something to everything, give everybody $5, it shifts everything. Right? It doesn't necessarily spread things out anymore. So just a constant change, right? Like the fixed cost. Instead of being minus 100, if the cost is $200 and it was minus 200, that wouldn't change the variability of the result. It would shift the average down by 100. Yes.
Wouldn't only the b times expectation of x b squared?
This thing is, so let me make this one a little darker here. So this whole thing is all right out there. Right. So in the expectation, right, there's y minus the average, and that is squared. So we think that the values we can have, like the 0, 1, 0, 1, 2, 3, 4, is minus the average and square that deviation. Right? It gets at how far the points are from the center. So A is in here, right? Minus A minus A, that goes away. So that was Bx minus B times the expectation of X. But B's in there twice, right? We pull it, we can factor out B out of this, B times expectation, X minus its expectation. And if we can have all of this inside the square. Well, if we pull that B outside of that square, right, you get B squared times X comes out of there. So what do you think we can do with that b squared? Expectation is a linear operator, so if we're multiplying by something, b is a number, b is a number, b squared is a number. We can just pull that b squared all the way out. Multiply by 5, right? On the expectation of something, it's like 5 times the expectation. You either can do multiply by a number and then expectation, or you can do expectation and then multiply by a number. So you can do it either way. So this is b squared times the expectation of x minus the expectation of x 1b squared. And what's that? That was our formula for variance, right? So that's the formula for the variance of x. So if you're doing a linear transformation, if you're adding something and then multiplying, right? The thing you're adding by doesn't change spread, doesn't change variance at all, right? It just shifts things like a constant amount. If you scale it, right, the square of that scale impacts variance. So in a predictable way. Let's do a variance calculation then 2 ways. So in this oil example, so the first oil example, we have 1,000 with probability 0.1 or negative 100 with probability 0.9. The expected value of the first oil example was $10. So what's the variance in this first oil revenue situation? Right, it says, the formula says, take the value minus the mean. So 1,000 minus 10 is 990 up here. This one's negative 100 minus 10 is negative 110. And we square those things, 990 squared, negative 110 squared, and multiply it by the probability. So we want 990 squared times 0.1 plus the negative 110 squared times 0.9, and that's going to be our variance. I'm not sure if I have that one exactly calculated, but let's get it on the computer, right? So eventually we're going to do more with this R program, and this is somewhat what it looks like. There's this console portion in here, and on Tuesday we'll do more with installing the program and starting it up, and it would be used on the following homework for some simulation and computation, right? Right, so we need 990 squared, right, times 0.1, and then there's a negative 110 squared times 0.9. So we're getting a variance of 108,900. Right? But that's on dollars squared, right? Variance is square everything. So the standard deviation is the square root of that. And square root, this is the command for square root. So we get a standard deviation of $330 right? In this one. So 108,900. This thing is 108,900. And the standard deviation of revenue in the first oil situation is the square root of that. 108,900. $330. So that's if we went to Y. I mean the dollar variable. We know that there's a relationship between just the success 0, 1 and the dollars. So would it be easier to figure out the variance with the transformation? Let's think about that. So in general, a Bernoulli random variable has a value of 0, 1, and the probabilities of p and 1 minus p. We figured out, maybe I'll just call this variable p. Right, I'll give it the name p. The expected value of this variable we figured out is 1 times p plus 0 times 1 minus p is simply p, the proportion. We had a bunch of zeros and ones. The proportion of times in the long run that you're going to get ones is p. What's the variance of this? What do we do to calculate variance? The values minus the means. There's two values, 1 and 0. Subtract the mean, which is p, and square it. And then multiply those squared deviations by the fraction of times you get 1 or the fraction of times you get 0. So you can get a 1 minus p squared times its probability that it happens, and then a 0 minus p squared times the probability it happens. And that's the variance formula for Bernoulli. I can simplify a little bit, right? 1 minus p squared times p. 0 minus p squared, right? It's negative p squared. The negatives go away, you just get p squared times 1 minus p. Can you simplify that last expression there? When you have something like that in symbols, right? What can you factor out of both terms?
1 minus p.
1 minus p and p, right? So if you factor out p and 1 minus p, right, what's left over? What's left over in the first term? 1 minus p. And what's left over in the second term? P. P, right? So that's just 1. 1 minus p plus p. So the variance of a Bernoulli random variable is just p times 1 minus p. So whatever the proportion is, as a proportion of 0.5, the variance is 1/2, or 1/4, 1/2 times 1/2, right? If the variance, if the proportion is 1/9, right, then it's 1/9 times 8/9, then it's 8/81, about 1/10, right? In this case, in the oil case, the success that we had was 10% of the time, and failure, which is 0, was 90% of the time. So the expected value of this variable, whether we're successful or not, is not that line with 0.1. What's the variance? P times 1 minus p, right? In general, this is p and this is 1 minus p. The variance is p times 1 minus p of this one. So 0.1 times 0.9, so it's 0.09. The standard deviation of a variable is the square root of the variance. So in this case, the standard deviation of a Bernoulli is the square root of p times 1 minus p. The square root of 0.09 is actually 0.3. deviation of 0.3. What was our equation for going to, from thinking about the success or failure into the dollars in this case? So we had y is negative 100 plus 1100 times, I guess x we call it. Success or failure is 0, 1 dollars in y. That was our transformation. So what's the variance on the dollar scale, or the dollar squared scale? Right? How can we figure out variance this way? So this was our transformation. Right? So going back, right, where was the transformation? That was directly calculating it. We had that the variance of a variable, once if you're coming from a linear transformation, is it's the slope, or the multiplier, is b squared times the variance. So in this FOIL case, b is 1100. So it should be 1100 squared times the variance of x. So 1100 squared times the 0.09. That should give us the same value we had before, which was what, there, 108,900. It should be this. That's not too much easier to compute in this case, because there's only two values. However, if the variance of y is b squared times the variance of x, what's the standard deviation of y in relationship to the standard deviation of x? Take the square root of both sides. Right? You get one value of b here times the standard deviation of x. And in the general case, b might have been negative. We might have taken a negative slope. I mean, that's possible in some applications. So technically, you do put an absolute value there, because we want standard deviations that make your spread to be positive. So in this case, our multiplier is 1100, and our standard deviation of x is pretty, once you know that formula, that's p times 1 minus p. 0.1 times 0.9 is 0.09. Square root of that is 0.3, right? Times 0.3, and we get 330. And that was the standard deviation on the dollar scale. So to do the standard deviation directly from y, I needed the computer. I can't do that in my head. Right? You can do it with pen and paper if you wanted to keep track of basically squaring these two numbers, right, and multiplying. But then you get 108,900, and you take the square root of that. So that's, you're going to use a calculator or something for that. However, if you're sitting around without your calculator on you, or maybe you have a phone these days, right? Where is it? It's pretty easy to figure out the variance of a Bernoulli, that is just the standard deviation just 0.3. So then the standard deviation on the y variable is much easier to do. Right? You're dealing with, you have all these dollars and you want to change them to, Bitcoins or some other funny currency, right? Again, you could scale this, and the standard deviation on the new scale would be the relative multiplier to get to that scale. On there. So we get that that transformation. But any questions?
How do you know that something's a Bernoulli? Like, what does that mean?
So the Bernoulli is kind of a model, right? So we'll talk about certain kind of examples that come up a lot. And so if something can be classified as success or failure, right, then it's going to have those two values. And this one's going to occur with some probability or 1 minus b. Right? So you're randomly picking people and asking them, did they graduate from high school? Right? It's yes or no answer. They might refuse to tell you, but really there's a yes or no underlying it. And for a defined population, there's a certain percentage yes, and that's the probability, and a certain percentage no. And if you're going on a testing lake, right, and you're taking an environmental measurement, is the pH above 5? Or between 5 and 10, like kind of in a more healthier range. Not too acidic and not too alkaline, right? But kind of in that range. If your outcome that you're measuring is success, okay, like basically okay, versus extreme, and has those two levels, then P would be the probability that a lake is okay, within tolerance levels of okay. And the zeros would be that it's bad one way or the other. Once you start recording things in a little more detail, right, actually recording the pH number, right, then it goes out of that model. You're recording more information. We'll do other variables, other kind of models or typical cases like this. And the thing that we can do with these kind of these few cases, right, is, for this type of situation, we know the expectation is the same as the proportion. The variance is P times 1 minus P. And so if it fits that scenario and we have some idea of that proportion, then we know something about it. And if that translates into number of P, you're scaling it some way, then you can get that other thing, right? Let's look a little bit more at the computer, since I gave you this handout. Part of this is just to introduce a few commands that we could use at later times. Does everybody have a copy of the handout? Everybody was filling that one out. So on this computer, I've installed these programs, R and RStudio, and when I just click on this one, it pops open, and the RStudio is kind of a graphical interface that is kind of nice and has some nice features. And when it initially starts, it looks something like this. This is just the console. Control L will take all that stuff away. And this is where you type commands. So if you type, like 5 or 3, you get those numbers back. You can do, 5 times 3 shows you this. You can save some of that information into, this is a little assignment thing, right? Way to say that. So we had 3 and 5 and 10. Now we have some object here that has those values in there, and so x can have those objects. So if we take x times 7, it's going to take 7 times each of those values there. We can take the first value is 3. We can take, say, the first 2 values in here. You can take subsets, so you can manipulate things in there, and so on. I'm going to get out of this one. Right? So I had started one before, and right. So what I had, we can even just start all this. Right? So in my folder for my lecture notes, I had this little thing, this RScript file. Now it's a certain type of file. I'm putting that RScript label in there because that's to keep track of what it is. On this one, I can open it. See, if I open it with RStudio, that set of commands will just pop into that top part up there, and I have some commands. Again, this console down here is where I'm going to type my things to get things to work. Up here, this RScript, you can start new RScript files, as you wish. So here is my new RScript file, and you can type things up here. And the thing is that if you save that, you can either do Control S or hit this little save file. Right, it's going to save it here. So my new RScript file. Right, and it's saved down here in this list of things. Right? So if I had a bunch of commands and things that I wanted to do, if I'm doing some of the homework or doing a senior project or some other thing for a class, and you type a bunch of commands, you can save them. So the next time you go to it, you can do that. Right, keep it. So here's one. You can make some graphs to show probability distributions. So things that are typed up here, if I highlight them or just have my cursor beside that and press this run, it moves it down here and makes a little graph. And I can make this one a little bit bigger to see it. So this was the car window probabilities, right, from that initial example. And I can put little titles on this. You can manipulate things, make it nice. This would illustrate the probability distribution. Now, there's a sample command. Right? 0 through 4 is its little way of getting 4 numbers in a sequence. Right? You know, so 9 through 12 would you give you those 4 numbers. You can make that as long or as big. You can make it go, you know, 10 down to -1, and it will go down in case you wanted that. Sample is a built-in command for sampling. Right? So if I want to sample from the numbers 0 through 4, and I put just one number in there, it's just going to pick one number for me. And it's going to change as I keep doing this. You can do arrow keys to cycle back and forth through the commands down there, so that's kind of nice. So if I type samp, you know, 0 through 4, oh, you know, I couldn't find that, but I can just click the key up and then edit that and fix it. Let's see, this command actually is kind of long. I made things a little bit bigger. If you sample, you know, from the numbers 0 through 4 2 times, you get 2 different numbers, right? If I do it 4 times, I get 4 different numbers, or 5, right? The default is to sample without replacement. Pick 5 different numbers. Right? If I do it, you know, 10 times, it's going to say there's a problem because I only had 5 numbers. And if I pick without replacement, then it runs out. So you can tell it replace equals true, and it will pick from those 5 numbers with replacement. So you can do as many as you like. There's actually a help file for these commands. You do help, and here's a help file that tells you a little bit about the form of the command, kind of the syntax. And, we won't use a huge number of commands, but you know, there's a few examples for things down there. You can toggle between these different windows that are in here. So here's my plot again, help file if I want to go back to it, and so on. But as the sample help here says, right, you can put probabilities in there. So I can put in my probabilities of 0, 1, 2, 3, and 4 in there, and then sample in those probabilities. So I'm going to copy, oops, Control Z undoes some of your mistakes in there. So I'm going to copy that, Control Z, and go down here and Control Paste. I'm not going to do it 1,000 times. I'm going to do it 10 times, right? And I get 10 numbers. Here's a different 10. Here's another different 10. Right? And I guess what you might be seeing is that, you know, the 0, 1, 2s and 3s are not coming up nearly as much, right? But if you do this 1,000 times, there's a table command. And what would be make a little table of those thousands. So here we go. Right? So it sampled 1,000 times from that distribution and tabulated the number of 0s, 1s, and 2s. So you can get a little sample from that. Right? It's pretty fast, so you could make this, you know, 100,000 times, and that's how many 0s, 1s, and 2s. At about 40%, that's getting pretty near to 40% are 0s, pretty much 20% are 1s, with a little bit of variability. If I do it again, it's a little bit less. At some point, I'm going to get more than 40,000 zeros. Yeah, see there, eventually I got a little bit more, right? But it's pretty close to those frequencies. If I did it 100 million times, right, it'd be very close to that percentage, right? And if you tabulate it, you can make this a bar plot of what that type of sample looks like. Right? So it looks like the probability distribution, the theoretical probabilities underneath, but it's based on a sample. If I did it again, it's going to change a little bit, but mostly be consistent with those probabilities that are under there. So probabilities, I work a lot of things in statistics and applied statistics. To me, the probabilities then translate into measurements, and often I have data and I want to infer what those probabilities are and kind of go the other way. This course is mostly about thinking about the consequences of probabilities and what it will mean for measurements we might get. So we'll kind of go that way. If I put this in the middle of this, I can add a nice little title on there. Right? We didn't do that example. Here's the tagging questions. Right, so say you had a population of size 100 and you went out and tagged 10 individuals. Right? Well, the number of ways you can choose 100 out of 10 is very large, 10 to the 13th in there. And say that 40 were tagged and 60 were untagged, if those happen to be numbers. Right? Now you go out and get 10 more. what's the chance that you would have 5 tagged and 5 untagged in that? Right? So the answer to that problem, it would be computed that the choose are combinatorics, and about 20%. One reason we're going to use this is that there's built-in functions for a bunch of these random variables. Right? So the hypergeometric, it's called hypergeometric. So this type of random variable also is essentially kind of like a model. Right? So if you're in a measurement situation where you have a population or a group, and some of them are one type and another type, and you're sampling with replacement from the group, and asking how many are a case, you have it's a certain probability structure, right? Certain rules for calculating the probabilities the outcomes apply, and I think about that as a model or something that is a probability distribution. It's called hypergeometric, is the name that is given on it. And so there's a function here for computing the densities or probabilities, right? So it gets that same number. You can do help of that there. And so density, distribution function, quantile function, and some other things, random numbers, right, that are there. And certain things go into it. So x is like the number that you want. Is it 5 out of the 10? M is the new sample. Right? And N and K here are the numbers that split the population. We don't always use exactly the same letters that we use in our book. And there's just no universal consistency for some of those things. Right? But for instance, if you want to look at the probabilities of all the different outcomes, you're going to take 10 new ones. What's the chance you get nobody that's tagged, or 1 that's tagged, or 2 that's tagged in this situation? Right? You could calculate all those probabilities under this situation. It reports it to, in scientific notation. We can round that, so maybe we can understand what those are a little bit better. Right? And we can maybe let's try to round it to 3 digits. Right, so 0, the number 0 through 10, right? The probability of 0 out of 10, 1 out of 10, 2 out of 10, 3 out of 10, 4 out of 10, and so on, can be computed within the program. And if you wanted to see what that looked like, you can do a little plot. Right, here's the number 0 through 10, here's the densities or probabilities, and so you can see that if the population really was split into 40 and 60, you would get that picture. Okay? And you'd most likely get 4 or 6 or something like that. 4, 5, 6. Around that area would be the new tag. Right? However, if you had a population that had 400 individuals in it, it was a bigger population. Right? You go out and tag 40. There's 360 wandering around you've never seen. Right? You wait a little while, and then you go and randomly capture 10. What's the probability you're going to have 5 in that new sample? Now being tagged is much rarer in that. You can calculate those things. It does some numerical tricks actually for calculating this, right? Because those numbers are so big. But it gets a tiny probability. You're very unlikely to get 5, right, out of the new 10 because it's so rare that you've tagged. The population's so big. If you plot those things, right? This was the old one. This is the new one. Right? That in the sample, the red ones here, where there was 400 in the population and you tagged 40. Most likely, you're going to get 0, 1, 2, maybe 3 of individuals in that sample. So it's going to be much smaller. So the fact that you get a small repeat implies it corresponds to a big population, and there's ways to estimate that. So you can make nice graphs, look at these distributions, and learn different things there. Right? Yes?
If you just know how many you tagged the first time, and then how many you double tagged after the second time,
Yeah.
how easy is it to reverse engineer the population size?
Yeah, so it's a pretty standard thing that gets done, right? So within that problem, if it's in a 2x2 table, right? And so this is the first survey. And so tag, untag. And say you had 40 individuals and 60 here out of the 100. So you tag a pretty big portion of the population. Right? And then you do a second survey. Right? And some are tagged and some are untagged in this, right? And let's say you just take 10 and you get 5 are tagged and 5 are untagged. So the numbers you know are this and this, where you take 40 in the first survey, right? You pick 40, you tag 5. Oh, wait, so you tag all 40. And then you take 10, that's the second survey, so you know that number. And then 5 of those individuals are matched, right? So that means that 5 were not tagged in the first, but tagged in the second. And that means that 35 were found the first time, but not located. So if, right, so 40 out of n, say that's our number, right, for the fractions, we got 40, we don't know, this is n. If the capture rate here, the 5 out of 10 is the same, right, how does it go? That if you got the probability of being here, if they're independent, well, not 100. So we picked 10 out of the probability you captured twice is 40 out of the total number, and then 10 out of the total number. Right? How many would you expect to be captured? N times that probability, and that it ends up being 5. So you cancel one of these n's, right? And so and solve for that. So 40 times 10 over 5 equals n. And so n, an estimate here would be this. Now this happens to be 400 over 5 is 80. So you get a prediction of what it is. It's off a little bit, right? But it gives some guidance in there. But it has to do, are the rates, is it independent in the different captures and so on? And can you match these individuals? If they lost their tag or something, you couldn't tag them. You could estimate the total. So this is sometimes called dual system estimation or capture, it's capture recapture, basic estimation of that. So. Okay. So on Tuesday, we'll do more with the computer program and we're looking at Android. Thank you.
Under.
You got a different one?
Hello, can I possibly ask you just a quick question on the wording?
What's wrong?
So the
When R1
problem,
pops up.
where you define the operation,
Yeah.
so for example,
I sent her a snap, so we were trying to push through because we didn't
is
talk
that
for a year and a half.
conditional? Like,
and we
well,
talked
I guess my first question is this a subset of the population exposed to risk, or is
Yes,
there
I believe so.
technically?
So I think 118 out of the 180 died.
Okay, so it's not total males is around 300, whatever that summation
Uh-huh.
would be. It would be 118 out of 180.
I believe so,
Is the
yes.
deaths? Okay. So then, a male in first class dying, is it then 118 over the total people in first class, or like 118 males out of all the males who died?
So maybe 118 out of the 180. So in the first class,
Okay.
118 out of 180, that's the proportion of males that died.